Hello fellow viewers, so I wanted to post this video earlier today, but I realized that my microphone was off and I ended up not recording my voice, so my bad. But anyways, today we're going to talk a little bit about exponential functions and logarithmic functions. So let's jump straight into the topic. So for exponential functions, the equation goes a little bit like y equals to a x to the power of x, yeah? So few rules that a has to follow is that a has to be more than 0 and a cannot equal to 1. We'll get into that in a while, but first let's focus on this. So an exponential function can look a little bit like this. Two different graphs. For this one we call this an exponential growth, and for this one we call it an exponential decay. Okay, I think you can infer this for yourself, because a growth is just increasing upwards and a decay is just going downwards, yeah? Okay, so for an exponential growth to occur, your a has to be more than 1. Alright, so let's just make a equal to 2 for now. So I'll end up getting y equals to 2 to the power of x. Alright, as for an exponential decay, my a has to be more than 0 but also lesser than 1. So I can just write a as 0.5 for example for now. So y equals to 0.5 to the power of x. Now what I'm going to do is I'm going to substitute in a few values of x. So x equals 0, x equals to 1, x equals to 2, x equals to 3. These 4 values. So what I'll end up getting is y equals to 2 to the power of 0, which is 1. Y equals to 2 to the power of 1, which is 2. Sorry, that was an ugly 2. Y equals to 2 to the power of 2, which is 4. And y equals to 2 to the power of 3, which is 8. Alright? Now we move on to the decay. So we then up get... Oops, my bad. Okay. Decay. So we end up getting y equals to 0.5 to the power of 0, which is 1. Y equals to 0.5 to the power of 1, which is 0.5. Y equals to 0.5 to the power of 2, which is 0.25. Y equals to 0.5 to the power of 3, which is 0.125. Okay, that's end up what we'll be getting. So what I want you to do now is to notice the difference between these final numbers here. Alright, so from 1 to 2 the difference is 1. From 2 to 4 the difference is 2. From 4 to 8 the difference is 4. So what you see there is that the difference between the numbers is gradually increasing, and then it sharply increases. Looks kind of like the exponential growth over here. And that's how we get this answer, because as the x value increases, the y value increases as well, but it increases exponentially. That means it just gradually increases and then sharp. Yeah? Okay, let's do for the decay. So for the decay, the difference between them here is 0.5, and here is 0.25, and here is 0.125. Alright? So as you can see, the difference between these numbers as the x value increases, the difference between the y value will start to decrease. So it starts looking like one another. So what we'll be ending up getting is, as the x value increases, y value sharply decreases the difference, and then the gradual. So that will end up getting us our decay here, which is our purple one. Yeah? So that's how we derive from this. Now, for all exponential functions, for all of these, y equals to a to the power of x, they will all intersect the y-axis at 0, 1. Okay, why is that so? Because, okay, let's substitute x equals to 0, which we already have done, which our y value is always 1, because any number to the power of 0 is just 1. And therefore, our y value will equal to 1. Alright? So that's for exponential functions. Now let's move on to logarithmic functions. It looks a little bit like the exponential functions, but flipped over onto its side. Yeah, so just pretend a car. Yeah, that's a car. Yeah, let's just pretend that's a car. Okay, let's go erase this now. So we have this car. This is the, let's just say, exponential functions. But then as it is driving, it gets flipped over to the side. Boom. And now it's a logarithmic function. So basically everything we learned there just now for the exponential functions is now just on its side. So with that out of the way, let's take a look at this here. So over here I have a logarithmic function example, but I just flipped it to its side so it looks a little bit like what we saw in the exponential function just now. So instead of this x up here, I just want you to imagine as a y, like how we normally view it. And we will know that our x-axis will be here. But instead of our numbers ascending from left to right, we'll have our numbers ascending from right to left. So let's just say the negative integers are over here and then positive integers are there. Alright, you got that? Okay. Then I just want you to just soak yourself to the fact that the x value is on top now and the y value is on where the x-axis is supposed to be. Okay, so what you notice from this is that from our exponential growth and decay examples, we know that usually when the x-axis is ascending from right to left, the growth is going this direction and our decay is going from this direction. But since our y value, since we are ascending from right to left now, our growth will be from here to up there, and our decay will be from here to down there. Because here will be the negative numbers and here will be the positive numbers. Alright, so let's do in some examples. So the equation for logarithmic functions is actually just y equals to log base a x. And if you work this out, you'll actually get x equals to a to the power of y. So it's almost the same as exponential functions, just that the values of y and x are flipped now. And that's why this is also flipped. It's like the car example. Alright, so let's do this. So it's the same thing as just now. For the growing portion, for the increasing portion, your a has to be more than 1. It also has the same rules it has to apply. A has to be more than 0 and a has not to be equal to 1. And for a decrease, it's this one. Same as before. Alright? So I'm just gonna make it a equals to 2, a equals to 0.5. Same as just now so you don't get confused yet. So we'll get y equals to log 2x and y equals to log 0.5x. Alright, then we're going to substitute in the same values as just now. So we're going to substitute x equals 0, x equals 1, x equals 2 and x equals to 3. These are just examples. I'm just going to substitute in them. So what we'll end up getting is y equals to log 2, 0, which will give us... Hold on, I'm a little bit rusty over the holidays. Haven't been revising my stuff. Okay, apparently you can't do that. Okay, we'll not do this one. Okay, we'll just start from 1. So when x equals to 1, so we'll end up getting y equals to log 2 to 1. We'll get 0. Alright, then when y equals to log 0.51, we also get 0. Y equals to log 2, base 2 will get 1. Y equals to log 0.52 will get negative 1. Y equals to log 2, 3, and we'll get 1.58496, and for this one y equals to log 0.53 we'll get the inverse of what we got before. Wait. Oh no, I ran out of space. Okay, let's just pretend I have space there. So same as before, notice the difference. Here is just 1 and here is just 0.58 and it goes on. So same for here, just that it's decreasing. So for the increase, as you can see, as the x value increases, the y value also increases, but it increases the difference between the increase is getting lesser and lesser. So at first, the y value will be like, oh, great increase. But then after that, as the x value goes on, as the x value goes on, the decrease gets gradual and gradual and gradual. Yeah. As for the decay, as the x value increases, the decrease is very big. So it's like, dig down deep. But then as the x value increases more and more, the difference gets lesser and lesser, so it will just be a gradual decrease. Something like that. So that corresponds to what we have on the graph. Alright? The last thing I want to cover for today's video is why a cannot equal to 1. So yeah, we have substituted, wait, hold on. Yeah, okay. So for the exponential functions, let's do that first. If I substitute a equals to 1, I'll end up getting y equals to 1 to the power of x. Then for the logarithmic functions, if I substitute a equals to 1, I'll end up getting y equals to log 1 x. And from this, we actually know that it's not possible because the base must be an integer, which is more than must be a whole number more than, wait, sorry, my bad. Okay, I'm tripping. A must be a number more than 0, but it cannot equal to 1. Yeah, that's the rule. And as for this one, we know that 1 to the power of anything is just 1. So we'll end up getting y equals to 1, which is not an exponential function. It is just a straight horizontal line intersecting y at 1. Alright, so I hope that does it for today. So thanks for watching.